Well, good morning, everybody, and thank you for joining us for this first MVHR Masterclass. Um, as you may or may not know, this is a new format for us where we're going to take a little bit of a deeper dive into the technologies that Mesh typically specify. And because this is the first time that we've run this presentation, I would be very grateful if at the end you could fill in the feedback forms so that we know how to improve it for next time. And also just so that we know if we've sort of got the pitch level at the right sort of mark for what you guys are expecting. So without further ado, I will crack on. There will be a section for questions at the end, so please feel free to type your questions into the comment box in Zoom, and at the end we'll go through and we'll try and pick out as many questions as we can, so that you all know what's so you've all got an opportunity to clarify anything that you're not quite sure about. Okay, so just going to go through what we're going to cover today. So with the introduction, we'll do a little bit about who Mesh Energy are, what we do, and where we've come from. Then a little short section about what MVHR is. Hopefully, if you've signed up for this, most of you will know what that is, but we will cover it because we want to make it complete. Then we'll have a little look at what natural ventilation versus MVHR. There's obviously mechanical exhaust ventilation that sort of sits in the middle of that, but we'll just try and simplify it by just having the two. And then we're going to go on to this sort of main part of the presentation, which will look a little bit more in detail at some of the specification and design issues around MVHR. So that's the building regulations and passive house ventilation rates, some space considerations, air tightness, ductwork layouts and types. That's quite important because as most of you are architects, that will be the bit that affects you guys the most in terms of allowing space and things. And then a little bit about filtration, what the filters do, where they are in the system, noise, and then things like electrical supply and running costs. And finally, condensate, which is something that people sort of quite often forget about, but it just needs to be allowed for. So we'll talk a little bit about that. And then the sort of third part of the presentation is the next steps. So just pick up a few of the key points from the presentation, then look a little bit about how we can work together with Mesh and the similar consultancies. And then finally, this question section at the end. So that's very briefly what we're going to run through. So without further ado, let's get going. So who are Mesh Energy? Well, Mesh Energy are your partner in low carbon future. So we're an independent consultancy. We aim to give sort of non-biased advice on what the best way of heating, cooling, and generally designing mechanical services for buildings are. And that's everything from initial design stage all the way through to sort of post-occupancy evaluation. But what we aim to do is we aim to be holistic and impartial. So we won't recommend a technology just because we have a tie-up with a manufacturer or something, because we don't have those. It's quite simple. We just try and give you the best possible advice and give you the sort of best advice at every stage of the project. Okay, that's that bit done. Now we can crack on with the actual engineering. So let's first of all look at what is MVHR. What does it stand for? It's something that people hear bandied around quite a lot. And very simply, it is mechanical ventilation with heat recovery. So it's as I've tried to sort of demonstrate with these icons here, it's mechanical. It uses a big fan effectively or a couple of big fans to blow air around the house and to suck air out of the house. It provides ventilation, which obviously is crucial to maintaining a good indoor environment. It harvests heat, so rather than the heat that is being produced by the heating system or through heat gains in the building, being wasted during winter time, that heat is recovered and reused. So it's a recycling system for heat. And how does it do that? Well, it does it through a clever heat exchanger, where the cold outside air is preheated using the heat from the warm stale air which is being extracted from the house, and that happens in a big box or several big boxes. So here's a little bit more of a formal definition. So MVHR systems extract warm, damp air from the home and draw in fresh air from the outside. This is obviously a domestic definition, but equally this can be applied to commercial buildings, office buildings, and any building which has got reasonable air tightness. And then that extracted air is passed through a heat exchanger, the heat is recovered, and then that stale air is expelled, and the fresh, cool air is brought into the other side of the heat exchanger, so it doesn't come in contact with the exhaust air, it doesn't mix, but it's pre-warmed by that heat exchanger and then circulated around the property. So let's have a little look at natural ventilation. Here's a sort of basic overview. It shows a couple of open windows. That may well be trickle vents, but effectively what you're doing is you're allowing for the air to pass through the building through dedicated ventilation channels. And this is the way that the houses have been traditionally designed, and how an awful lot of new builds are still built. You design the openings carefully. You still build the house as quite airtight, but by having those openings, you allow ventilation in the areas that it needs to be. And then, thanks to the natural pressure differences between the inside and outside air, thanks to things like wind, you'll get a movement of air through the property, which should give you the required ventilation rates in each room. It's worth noting at this stage that if you start looking forward to things like REBA 2030, which is obviously not that far away on the horizon now, we don't think it's possible to meet the requirements of REBA 2030 without using MVHR. So natural ventilation, whilst it's very effective, very well proven, we don't think it will be fit for purpose on the next generation of buildings. So here's another natural ventilation scenario. This is single-sided. You might quite often see in a block of flats or something, or in a larger development where you've got a single aspect. So you got these are notoriously poor in terms of ventilation, which is why I've used that particular image on this slide. But the disbenefits or the sort of the downsides of natural ventilation is that it can be quite uncontrolled. So it can vary from room to room quite a lot, even if you've got the same size ventilators on the windows, just because of things like the natural wind direction, prevailing winds, prevailing pressure differences, other things within the house can cause you to get quite different ventilation rates from one room to the next. The performance can vary with atmospheric conditions. It's something that people often don't think about, but obviously you tend to design a natural ventilation system with the prevailing wind in mind. But as you know, as we've all experienced in the last few days, it went from being really quite chilly with a northeasterly kind of prevailing wind over a few days last week, to being reasonably warm again this week, and that's because the wind has now come from a different direction, and that will affect the performance of natural ventilation systems. Obviously, if you get the design wrong, it can also lead to drafts, especially if you're looking at things like having open fires or stoves. You can really suffer from drafts, and because you're not recovering the heat that's going out with a natural ventilation system, on a very well insulated building, the ventilation heat losses, which is the amount of energy you're using to heat the air within the building rather than the building itself, can actually equal the fabric heat losses. So there's quite quite a significant chunk of money that people are spending. Benefits of natural ventilation: obviously there's zero running cost, or zero direct running cost. With natural ventilation, you're not running a fan, you're not running, you're not having to run any sort of preheaters, you're not having to change filters, you're not having to do anything of that kind of stuff. So it's got zero direct running cost. Obviously there's quite a significant indirect running cost from increased heating bills. It's relatively easy to specify. It's about making sure the right ventilators are in the right place, and there's obviously no noise associated with it because there's no fans, there's no mechanical items that can make noise. So let's contrast that with mechanical ventilation with heat recovery. So on the right hand side here we've got a sort of typical trunk and branch type MVHR system. A picture of an MVHR unit in the middle here. It runs on electricity, so clearly there's going to be a running cost associated with it, but it recovers waste heat from the exhaust air, and because of that, it actually offers relatively low running costs. In fact, in most cases, what you will save in heating costs will more than offset the additional electricity that you'll use, and we'll look a little bit more detail about that in a minute. And a well-designed system should be very quiet. As a rule of thumb, you can see a 30% reduction in heat loss when you're looking at an MVHR based system versus a natural ventilation system for the same building, where air tightness is reasonably good. So here's a typical MVHR unit, and it shows all the sort of major ducts going in and out. So you've got 4 ducts. Effectively, one is going to the supply ducting, one is coming back from the exhaust, from the extracts, and then you've got a duct coming in from the outside air and one going out to the outside air. So you've got 4 ducts you have to consider. Then you've got the filters, you've got the controller and the cover panel, and then right at the bottom you've got the condensate. So the downsides of a mechanical ventilation system: there's obviously additional cost of installation, there are obviously additional space requirements, and of course there is the maintenance of the system. Any mechanical system, your car, your washing machine, anything else requires some maintenance, and in this case most of the maintenance is changing those filters or inspecting those filters every sort of 3 to 6 months, and we'll look at that in a little bit more detail later on. The benefits: well, you can see a 30% heat loss reduction. It's obviously quite a big financial benefit potentially, because you're extracting 75 to 90+% of the heat from the air, and you get controlled building-wide ventilation. So you don't get any little, if it's well designed, you don't get any little dead spots where you're not getting air changes. All the rooms are adequately ventilated. No rooms are over-ventilated or under-ventilated. You just get a nice comfortable environment. One of the things I always say about heating is the best sort of measure of heating is if you don't notice it's there, then it's doing the right job, and the same should be true of MVHR. People who have MVHR say, well, I don't notice the fact I've got MVHR. What I notice is when I go to a house that doesn't have it, that I notice that it's not as comfortable, and that's really what you should be aiming for. So now we've had a sort of very quick, brief overview. Let's have a little look at a little bit more of the some of the sort of more detailed bits that go into an MVHR specification and design. And this is really where the mechanical services element and the architectural element really overlap, because there is no point in designing a beautiful looking building and then trying to shoehorn an MVHR system into it afterwards, because it simply doesn't work. So the first thing we need to look at is actually what's the aim of the system. We're trying to provide an adequate ventilation to each part of the house. So effectively what you're doing is you're supplying air to some rooms and you're extracting air from other rooms, and typically the rooms you extract air from are rooms where you're creating moisture. So that's bathrooms, kitchens, utility rooms, and also places like gyms and other places where you might, and sort of certain storerooms and things like that, boot rooms, those kind of things, where you might be putting wet clothing, you might be having showers or baths, where you're producing steam, you're cooking, where you're producing steam from cooking. That's where you'd extract from, and then you're basically supplying air to every other part of the building. And by doing that, you create an environment where air is moving from the habitable areas into the wet areas and then being taken away. That heat's then being extracted and is being then recirculated back into the living areas. So part F tries to cover that, and gives you a number of required supply ventilation rates, and those are shown in table 5.1b. And I've put a copy of table 5.1b in the top right hand corner there. It will be far too small for you to read, but obviously that's the sort of key table in ADF for MVHR. And actually, probably the most important thing in that table is actually one of the notes, which says that for most that you must provide 0.3 litres per second per metre squared on larger buildings, and for most houses, that's actually where you end up. That ends up being the lower limit, is this 0.3 litres per second per metre squared, if you're designing to ADF. Then it also gives you the required extract rates, and it lists them by room type. So it gives you different rates for bathrooms, kitchens, utility rooms, WCs, etc. And then you basically sum up all those requirements, and that tells you what your total extract rate minimum must be. And you sum up the total for the supply. And then basically what you want to do is you want to balance the supply and extract, because obviously what you don't want to be doing is sucking more air out of the house than you're putting in, or equally putting more air in than you're sucking out, because you'll end up with either a positive pressure or a negative pressure in the house. Ideally, you would like to see a very small pressure difference between inside and outside, so that you try and balance those two things together. And I've again put the table 5.1a, which is the extract rates table in there. Again, it will be too small to read, but those documents are available freely online. So here we go. Let's have a look at the Passiv Haus method. So the Passiv Haus method is slightly different, uses different units. So just be a little bit careful about that. Some of the units can get a bit confusing. But what they're aiming to do is they're aiming to maintain a good indoor air quality to IDA2. And they do that by saying that supply must be equal to 30 meters cubes per hour per occupant. So they're asking you to basically assess how many occupants there are in the house and do it that way, rather than doing it on a square meterage basis. They look at the air supply is required for each habitable room, which is pretty similar to part F. And then it gives you slightly different extract rates for the kitchen, bath and WC, but it also gives you a boost rate as well as a sort of standard rate. So it's a parallel method, not totally dissimilar, but it gives you slightly different results. So it's worth being aware of. And you'll notice this photo, this seemingly random photo I put of a bathroom here. And the reason I put it in is if you look up on the top right-hand corner, you'll see there's a vent up in the top right-hand corner. Rhiannon, can you still hear me? Because I've got a one thing saying that they've lost sound.
I can still hear you.
Good, okay.
We've had a few issues with people signing in as well, though. So.
Okay, well, hopefully the recording will be good.
I can still hear you.
Good.
If one of the participants would like to let us know whether or not you can still hear David.
I can still hear.
Excellent. Yeah. Okay, so I think I'm fortunate. Yeah, good. Okay, good. So do you want to just drop a note back to Toru in the chat, just saying it appears to be at her end, or his end, not sure. Toro, their end. Okay, sorry. Let's carry on. Right. So, space requirements. This is the biggest single thing that we battle with as a consultancy when specifying MVHR systems. Air is big, as in one word. So we need to allow space to move air around and for the MVHR plant. So that means ceiling voids need to be big enough to allow ductwork to run through them. We need to consider where the plant's going to go and allow enough space. We need to allow enough space for the typical duct sizes that are going to be used. And we also need to be able to consider clashes with the structure. And that's one of the places that quite often trips people up, is that they design in large ceiling voids, and then you have one steel that runs through the middle of that ceiling void, which obviously acts as a barrier, and unfortunately air can't pass through a steel particularly well. So we just have to be mindful of that all the way through the design process, is just considering any of those clashes. Ways around that, well, on larger projects, it's often worth considering using multiple units to reduce ductwork runs and ductwork sizes. What can you do? Well, a job I did quite recently, there were different wings to the house, so each wing had its own MVHR unit. That reduced the duct size, but it also meant that one of the wings was a sort of guest annex. It meant that we could set the guest annex ventilation rates back when it wasn't in use, and equally we could ramp up the extract rates and supply rates in the main bedroom wing, for example, when the bathrooms were in heavy use, and turn it down in other areas of the house when people were sort of getting up and going to bed. So it's often a good idea to try and zone MVHR units, sort of thinking about how the building might be used, rather than necessarily doing it floor by floor, or by doing it dividing the building vertically. There's different ways of doing that. And I just like to point out, that's not a domestic installation. I was just trying to make the point that sometimes ducts are quite big, so don't worry, they're not that big. Okay, so air tightness. Again, we're designing here to make sure that the air tightness is compatible with MVHR, and as we know, we're going to typically need MVHR to meet RIBA 2030. And we know that MVHR is likely to be beneficial on buildings, or will nearly always be beneficial on buildings where an air tightness is better than 3 meters cubed per meter squared per hour at 50 pascals. But it may also reduce emissions, reduce energy consumption, and hence emissions on buildings with air tightnesses up to around 5 meters cubed per meter squared per hour at 50 pascals. And the graph on the right hand side here, which although it's probably not particularly clear, is actually taken from a scientific study where they were looking at the effect of some models emissions from a building versus air permeability. And in that case, they found that particular building came out at around 5, where the crossover was between MVHR being beneficial to it being a disbenefit against natural ventilation. So you can see that it does vary slightly from building to building, but if you're designing to 3 meters cubed per hour per meter squared per hour or better, you're definitely going to need MVHR, or definitely going to benefit from MVHR. If you're between 3 and 5, you may benefit from it, and if you're above 5, it's unlikely you'll benefit from it. It's obviously possible to retrofit MVHR, but as I said, you get a reduced benefit on older, leakier buildings, so you might be better off concentrating on other areas of improving the building efficiency, such as increasing the air tightness, or just increasing the insulation. Okay, so let's have a look at some of the common ductwork arrangements, and let's have a look at some of the advantages and disadvantages of both. So this is this is, I guess, the type of ductwork arrangement that most people might immediately imagine with MVHR. It's called trunk and branch, and effectively what you have is you have one big header duct for your extract, one big header duct for your supply, and then you have branches off to each room that you're serving, and they all go back to the MVHR unit. There'd obviously be a couple of ducts going from here to the outside, and the sort of header duct will decrease in diameter. So that's the trunk will decrease in diameter the further you get from the MVHR unit, and the branches will be relatively similar sizes. They'll obviously vary slightly depending upon the size of the room they're serving. But basically, the greater the distance from the MVHR unit, the smaller this trunk duct becomes. These can be a really nice solution in certain properties, but obviously you've got this big duct that you've got to try and fit somewhere, and that can be problematic in certain designs. So the alternative to that is what they call a radial system. And in a radial system, you effectively have two big manifolds, an extract manifold and a supply manifold, and then you run individual ducts to each room from that manifold. So that manifold will be usually quite close to the MVHR unit, typically hidden in the ceiling, and then you run, say, a dedicated duct to each room. They can often be a bit quieter as well, this type of arrangement, because you can lower the duct velocity in each one of those little radial ducts, and air movement noise can be a bit of an issue if you start getting duct speeds above about 2 meters per second in the final ductwork. It can be simpler to install simply because you're tending to use a slightly different type of ductwork, which is a bit more flexible, and it also means that you don't get this the issue of crosstalk, which is where if there's a direct link between two rooms, particularly between bedrooms, the noise from one bedroom can travel through the ductwork into another bedroom or into another room. But I mean, that can be worked around using things like silencers, but it does eliminate it straight away. Okay, so next thing is the ductwork types. So we've looked at what those ductwork systems might look like as a sort of schematic. Then we also actually think about, well, what is the actual ductwork itself? And there's really three main sorts that are used in MVHR. The first of those, and probably the most traditional, is spiral wound galvanized steel. It's relatively cheap to buy. It's pretty flexible because you can cut sections on site. You can, skilled duct workers are absolutely amazing with the things they can do with this ductwork. It's typically available in round sections. The cheapest way of buying it is in round sections, but there are flat oval versions available as well. So people like Hotchkiss Design do rather nice flat oval ductwork. The standard you're looking for with this is DW144, which is the standard for specification for manufacturing and installation of sheet metal ductwork. The next type is PVC. So this is typically used as a replacement on a duct and branch system, on a trunk and branch system, where you have limited space.
David, I think.
Yeah. Go ahead, Rhiannon.
Oh, David, are you back?
Yeah, I've got some message actually just come up saying my internet connection is unstable.
Okay. If you, I'm not sure quite where you got to when you disappeared, but wasn't that far back.
Okay. So if I'll carry on from the beginning of PVC again, and then hopefully the BT gremlins will go away.
Apologies, everybody. We seem to be having a few technical issues this morning.
So hopefully everybody can still hear me. If you are awake and I haven't put you to sleep yet, then please feel free to put a comment in or a question in for later on. But unfortunately, this is the joys of doing webinars live over the internet. So let's have a quick look at PVC. So typically PVC ductwork is used on trunk and branch systems where space is a little bit more limited, because it's typically used in rectangular sections, although it can be brought in round as well. It just allows you to reduce the height of the ductwork a little bit more easily than you can with spiral wound. Some people do get concerned about the resistance. It does tend to give higher resistance than the equivalent round system ductwork, and also spiral ductwork, because the corners and things in it tend to be a little bit sharper. That can lead to noise issues, and it also can be slightly harder to clean, and it's not as resistant to things like mold growth as some other types of ductwork. So some people are less keen on using it for that reason as well. But generally speaking, it's quite widely used. There are a couple of companies that don't use it. And then finally, the other sort of major type of ductwork that's used in MVHR is what's called semi-rigid. It looks like a big sort of Hoover tube, for want of a better sort of analogy. Obviously larger in diameter. Typically this would be coated with an anti-mold coating on the inside, so cleaning is less of an issue. And it's used typically in radial systems. Because it's semi-rigid, it means it can be used to create small offsets without having to joint the system. And because you can create easy swept bends with it, that's good from a resistance point of view. The only things I would say is beware of resistance. If you try and reduce the diameter, you don't want to be introducing additional resistance. And also, obviously, when you reduce the diameter to get the same flow, you have to push the air through faster, which can lead to noise. The last type of ductwork, which I'm not going to cover in any great detail, is flexible ductwork. And the reason I'm not going to cover it is that it really should be avoided in MVHR systems. Flexible ductwork is very prone to being crushed. It decreases the system efficiency. It doesn't actually comply with Part F regulations, which states a maximum length of flexible ductwork in the MVHR system, which I can't remember what the dimension is, but it's not very long. It adds resistance, and because it adds resistance, it adds to noise potential as well. So please avoid using flexible ductwork in MVHR. So the next part is around filters. Now this is probably less of a design consideration from the architect's point of view, but one probably worth considering, because it's all about the air quality that's provided by an MVHR system versus a natural ventilation system. So in a typical house, you're obviously bringing fresh air in and passing it through a filter before it goes through the heat exchanger, and that allows you to get rid of certainly dust and grime from the air, but also depending on the type of filter, you can also get rid of pollen. So in terms of maintenance, the main sort of maintenance things are: you pull the filters out every 3 to 6 months and give them a quick hoover off, and then you would also replace the filters on an annual basis. The reason you do that is to stop any potential mold growth from dirty filters after a year. Filter replacement is fairly straightforward and can typically be done by the householder, but most MVHR installation companies will offer a service agreement as well with the system. The cost of the replacement filters themselves is typically around £50 for the system. And that's what a dirty filter looks like in comparison to a clean filter. Remember, these filters that I'm showing you here as dirty filters, that is dust and dirt that would otherwise be coming into the house through natural ventilation. So it's not additional dirt that's being generated by the system. This is actually dirt that's just simply not coming into your house in the first place. So those filters are divided into two sorts. The intake filters, so you generally have a pre-intake intake pre-filter, which protects any preheater. You then have an extract filter, which protects the heat exchanger from any debris that's being collected whilst the air's in the house. You then have an intake dust filter, which is slightly finer, a G4 or M5 type filter, which filters the air going into the house to make sure it's absolutely nice and clean. But then you can also, as an option, add an F7 filter. An F7 filter is a pollen filter. So when you had all those car adverts a few years ago and they talked about having pollen filters on the cabin, all it was is they'd just changed the filter that was there before, which was probably a G4, for an F7 filter. And those are an option on most MVHR appliances. Downsides of using a pollen filter is that it adds slightly to the resistance. So you have to specify a very slightly bigger unit to account for the extra resistance in the system. The other filter that is quite important is that in the kitchen where you're extracting, and please bear in mind that the extract from the kitchen is not the cooker hood, it's a different extract. So you'd have typically a recirculating cooker hood with its own dust and grease filters and air filters on it. But you will have an additional extract that goes back to the MVHR system in the kitchen. There should be a dust and grease filter, a G3 filter on there, and that's to protect the ductwork, which is just upstream of that, going back towards the MVHR unit. So noise attenuation. This is possibly the biggest fear people have of MVHR, much more so than than running costs. People are scared it's going to be noisy, and it won't be. A properly designed and implemented MVHR system should be whisper quiet. I mean, it really should be totally unnoticeable. Where there have been noisy systems, it's generally the result of poor design, poor installation, or poor commissioning. So how do we make sure that we don't get noise? Well, first of all, we make sure the MVHR unit itself is correctly sized. And that means we optimizing the fan speed so that it's not having to run absolutely flat out all the time, because that's when they tend to get noisy. You then minimize noise by good ductwork design. So that means getting the ductwork to a large enough size that you're keeping the air velocities down, so that you're not generating noise in the ductwork from air. Then you're minimizing noise between rooms by putting in strategically spaced silencers, or by using a radial system. And then you can also put in additional systems, particularly on areas that may be close to the unit where you might get noise, or where you've got maybe quite high airflows. You can use additional silencers to eliminate noise in those areas. And the final thing is the commissioning. Obviously, it's all very well designing a beautiful system, but if it's poorly commissioned and you don't have the airflow rates correct, then you might end up with unintended or unexpected noise. So that's all about good commissioning. But that also ties back to the design, because if you don't get the design right in the first place, it's going to be impossible to commission correctly. So it's important to get the design right. So electricity supply and running costs. Well, the good news is there's no special electricity supply required. Domestic MVHR units use very little electricity, so there's no requirement for power upgrades, anything silly like that. Typically, you just have a fuse spur or a dedicated radial circuit going out to your MVHR units. They will often use less than 100 watts. So you're talking about a tiny little circuit. and the efficiency gains in the heating vastly outweigh the running costs in airtight houses. One of the figures you might see when you're looking at MVHR units themselves is what they call the fan efficiency. So what that does is it looks at basically how much air is blown for each watt of electricity that goes in, and typically you're looking for a figure of sort of 0.7 watts per litres per second or better for a good unit. Obviously any improvement you make there is a direct benefit, but obviously the more expensive units tend to have better numbers, so it's always a bit of a sort of trade-off between cost between capital cost and running cost. But typically the cost of running an MVHR unit is around £100 a year for a 3-bedroom house. Is a sort of good value, good kind of running cost number. So finally, and this is the last part of the sort of specification part, is condensate drainage. So your MVHR unit will produce some condensate, especially during the winter. You will need to have a condensate drain to deal with that, which removes water that collects on the heat exchanger during normal operation. Domestic MVHR units will have that as a little drain on the bottom of it, and that drain should be connected to a waterless dry trap, which is similar to the one that's shown on the screen. The reason for that is that water-filled traps can dry out during the summer, and then you can get drain smells coming back up through into the unit. So it's much better to, if possible, have a waterless or dry trap used rather than a water-filled one. Okay, well that pretty much covers the sort of technical side, which I'm sure you'll be relieved at. So I'm just going to go through now the top 10 MVHR considerations. So if you remember nothing else from this presentation, try and remember these top 10 tips. So tip number 1, and I'd probably say if you're going to only remember one tip, remember this one: get the design in early. It's so much easier to integrate an MVHR design early in the life of the building rather than trying to shoehorn it in later. Consider how ducts are going to pass around the structure of the building. As I said to you earlier, ductwork and steels don't mix very well. So just consider how you're going to pass the structure. Remember to insulate the inlet and outlet ductwork to prevent interstitial condensation on the outside wall of the ducts. Allow for the condensate drainage from inside the unit. Remember that people are going to have to get to the units to service and change filters, so allow for that. Allow sufficient space for system balancing and commissioning. So that means also at the vents, make sure that there's an ability to balance the system. Allow for the silencers. Silencers are obviously a bit bigger than the standard ductwork, so just allow for that, and manifolds as well. If you're using a radial system, keep the MVHR system within the thermal envelope of the building. That will improve efficiency. Maintain separation between the inlet and outlet ducts so that you can't get short circuiting, so you can't get exhaust air being pulled back into the unit. And finally, keep the inlet ducts away from areas of pollution or strong winds. Again, that is so that you don't get any unpleasant smells, or you don't get any issues with the wind affecting the performance of the ductwork. Okay, that's it. 10 top tips. Hopefully that's convinced you that MVHR is going to be a good idea for most new builds going forward, which I think it probably is. So let's have a look at how we now work together to get these implemented. So at stage 1, probably the best thing to do is to get a feasibility study done, start looking at energy and SAP calculations. So how does it affect the energy, and then just red pen some drawings with where ducts are going to go, and just make sure there's sufficient space. When you're doing a detailed design and specification, and we can also do installer recommendations at that stage, because we know good installers, so we like to share that with our clients. when prices come back, review the tenders, check that they are actually compliant with the specification, and provide insight at installation stage. And finally, the bit that people often sort of miss out, but actually is really important, is getting that energy monitoring and air quality monitoring done. Because anything that's not been picked up at installation stage, for example, if the balancing is not quite right on the system, would be picked up by air quality monitoring. And also it's making sure that the householders are actually using the system to its best advantage, because there have been stories where that's not been done. Okay, so any questions? Please feel free to type them into the chat box. Is anybody still there? Or have I covered everything so well that there are no questions?
I just want to say thank you very much, David. It was very interesting and a lot of background to the principles I think most of us understand. Thank you.
Fantastic, thank you. Okay, well,
just to let everybody know, before David wraps up, obviously the follow-up email will come out, and the presentation slides and a link to the YouTube video will also go up, so that will come out by close of play today.
Fantastic. Well, thank you everybody who attended. I would ask you please, with that pack that Rhiannon will send out later on, there will be a little survey. Please do take a couple of minutes to fill it in, because it's a new presentation. Well, there's a question here from David. How effective is MVHR when delivered through floor grills? It's not something I've ever seen done, so I honestly couldn't answer that. Generally speaking, ceiling or wall-mounted grills are what are specified. I can't see a reason why it wouldn't be effective through floor grills. I guess the one thing you'd need to be very careful of is sort of things like positioning furniture around floor grills and that kind of thing, to make sure that you didn't block the outlets. But as I say, because it's something I've never seen done, I can't really answer that question, I'm afraid. Sorry. Thank you, Rob. Thank you, Angus, as well, for your kind words. If there's no more questions, then I'll wrap up. Thank you very much for your time, and have a great rest of your morning.